Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we are going to talk about defining acids and bases. So the first definition of acids and bases came from a chemist named Savant Arrhenius. In Arrhenius' model, he said that an acid is a substance that contains hydrogen and ionizes to produce hydrogen ions in solution. So a great example of this is HCl, or hydrochloric acid. So in solution, the H and the Cl split up into H plus and Cl minus. So the presence of that H plus, according to Arrhenius, makes it an acid. Now he said that a base is a substance that contains a hydroxide group and dissociates to produce a hydroxide ion in solution. So here we have NaOH, which is an ionic compound that in solution splits up into Na plus and that OH minus. So that presence of OH minus makes NaOH a base, according to Arrhenius. So the problem with Arrhenius's model is that it talks about H+, but in reality, H+ is just a proton. Hydrogen is made up of one proton and one electron, so when that electron is lost to make a cation, all I'm left with is one proton. But a proton isn't very stable. We don't like having, free protons just flying around. So in aqueous solution, H plus is going to react with water to form what we call hydronium. So here I have a diagram. I have a hydrogen ion and then the water. This hydrogen ion is going to attach onto the water, giving it its +1 charge. That is hydronium, H3O plus. This is more stable for the water to be, not for the water, for the proton to be connected to the water. So we talk about H plus and H3O plus synonymously. They mean exactly the same thing. In fact, chemists rarely even differentiate between the two. If I say H plus, I could have just as easily said H3O plus. It doesn't really matter which one I pick. It's just whichever one kind of comes to me in the moment. So now let's look at the definition of an acid in terms of using hydronium instead of just H+. So HCl, instead of just splitting up into H plus and Cl minus, that H plus is going to go directly onto that water to make my hydronium, H3O plus, and I'll be left with that Cl minus as well. So it's just slightly different, and you can see how it's pretty much the same thing, H plus versus H3O plus. But there's a bigger problem with the Arrhenius model. Ammonia, NH3, has the characteristics of a base. Right? We haven't talked about the characteristics yet. We will later in this video. But everything we know about ammonia says, hey, this is a base. The problem is it doesn't contain any hydroxide. I don't have a way for NH3 in solution to produce OH minus. Right? It can't dissociate to form OH minus ions. It doesn't even have oxygen in the molecule. This was a huge issue. So along came two other scientists, right? Bronsted and Lowry. So Bronsted and Lowry expanded on the Arrhenius model. So they didn't scrap it and start anew. They just changed the definitions a little bit. And this was all to explain why ammonia is a base, but it doesn't contain hydroxide. So an acid, according to Bronsted and Lowry, is going to be a hydrogen donor. A base is going to be a hydrogen acceptor. So now the definition of acid and base kind of go together. Now the acid is going to donate, the base is then going to accept that hydrogen. So we get this general equation, right? There's a lot of parts here and I don't want you to freak out. The HA on the left, this is just a generic way to represent an acid, right? And B is just a generic way to represent a base. It's not an element, it's just, well, the H is. The A and the B are just kind of fillers. So for an acid like HCl, the A is Cl. For something like HNO3, the A is NO3, right? So it's just kind of making us have a general formula. So the idea is this acid is going to donate its hydrogen to the base, like so. So now this hydrogen is now attached to the base, so we get Hb. Remember, this has that positive charge. So now I've got Hb plus. A has now lost that H and lost that charge, right? So now I've got Hb plus and A minus. So Hb plus is just a generic term for a base after it's reacted with an acid. So if my base was ammonia, NH3, then Hb plus would have another hydrogen and then a +1 charge. So from NH3, it'll go to NH4 plus. Right? So here is a way to explain ammonia. So I've got ammonia here, NH3, and then I'm going to react it with water, an acid. Now don't freak out, I'll explain why water is an acid a little later. So the acid is going to donate its hydrogen to the ammonia, and I'm going to be left with NH4 plus, and would you look at that, OH minus, right? Lost one hydrogen, lost one charge. So that's how I get hydroxide for ammonia. So Bronsted and Lowry's definition has explained ammonia, which was the whole point. So here's a combination of the two. According to Arrhenius, an acid is an H plus or an H3O plus producer, but according to Bronsted-Lowry, an acid is a proton H plus donor. Effectively, those definitions are the same, right? What's really different is the base. Arrhenius said bases are OH minus producers. Bronsted-Lowry was like, well, yes, but we want to be more general than that. We'll say it is a proton H plus acceptor. Right, so we are going to operate on the Bronsted-Lowry definition of acids and bases rather than the Arrhenius one. Okay, so conjugate acids and bases. So far, we're talking about this as happening in one direction, right? The hydrogen here donates to the B base. I've got an acid and a base, and everything is great. But that's only going in the forward direction. Acid-base reactions are actually reversible, which means that the reverse reaction also involves an acid and a base, right? To go back to reform what I had originally, this hydrogen is going to go back to that A minus. So now this is acting like an acid, and this A minus is acting like a base. Okay? So we have special names for this. The acid and base of the reverse reactions are called conjugate acids and bases. Right? Every acid has a conjugate base, and every base has a conjugate acid. They come in pairs. Right? It's like two sides of a coin. Right? If one side is acid, the other side is conjugate base. If one side is base, the other side is conjugate acid. So the conjugate base of HA, right, is going to be that A minus. Remember, this acted as a base in the reverse reaction. The conjugate acid of B is that HB plus, which acted like an acid in the reverse reaction. Notice how I've switched out that arrow is now a double-headed arrow. That's an equilibrium arrow, saying that this reaction can go in both directions. Right? So now every substance involved in this reaction has a title, right? Acid, base, conjugate base. Now, how do you find conjugate acid and bases if all you know is what acid and what base you have? You don't have a reaction in front of you, all you have is the coin. How do you know what's on the other side? So to get the conjugate base from the acid, I'm going to use my generic acid, HA. You're going to start by subtracting one hydrogen, subtracting one from the charge. So the conjugate base is A minus. Now, the conjugate acid from base, right, base B, you're going to add one hydrogen and add one to the charge. Right? For acid, you add. Right? There you go. You want conjugate acid, you add. And you end up getting HB plus. Right? One more hydrogen, one more charge. So in practice number 1 in your notes here, I'm going to take a second and pause for you guys. Go ahead and try to answer 1 and 2 on your own. When you're ready, go ahead and unpause the video and I will go over it with you. Alright, so hopefully you guys have had a chance to try 1 and 2 on your own. So number 1, what is the conjugate acid of ammonia, NH3? Well, if I'm trying to find the conjugate acid, I'm going to add. So I'll add one hydrogen, add one to the charge, I get NH4+. For number 2, what is the conjugate base of sulfuric acid? I'm going to subtract a hydrogen and one from the charge. So if I had 2 hydrogens, now I'm going to have 1 where I had no charge. Now I'm going to have a minus charge. Okay, just so 4 minus. Okay, so now looking at the reaction, right? Notice once again, this is just a different way to represent that equilibrium arrow. It means the same thing, that it's a reversible reaction. I'm now looking at a reaction cold. I have no idea what's acting as an acid, what's acting as a base. How do I know where the conjugates are? We're going to work through how we go about labeling each substance in this reaction. So I'm going to have two sides here. Right? Looking at each substance, what would happen if it acted as an acid? What would happen if it acted as a base? Right? So looking at NH3, if NH3 were an acid, right, acids donate their protons. So NH3 would lose a hydrogen and lose one charge. So I would make NH2 minus. Now, if it acted as a base, right, which secretly in the back of our heads we know ammonia is a base, it would gain a hydrogen and gain a charge, so we would see NH4 plus. So now I'm going to look at the product side and say, hey, which one of these do I see over there? And there's the NH4 plus. So I know that those two are conjugates. So right off the bat, I can label these two. Okay? The NH3 is the base, the NH4 is that base's conjugate acid. Now I'm going to look at the next part here, the water. If water acts as an acid, right, it would donate its hydrogen and lose one charge to make OH minus. If it were a base, it would gain, right? H3 and O plus. The one I see on the other side is the OH minus. So I know this is the acid, that's the other side of the coin, the conjugate base. Right? And I've labeled all four parts. Now here's another example, okay, where I'm going to actually simplify it. So looking at this, I've got HCl. On the other side here, I see that I have Cl minus. Well, hey, between HCl and Cl minus, I've lost a proton, so hey, that must have been an acid, right? I've made that Cl minus, so I've got an acid and a conjugate base here. Right? Now I can look at this and say, well, if that's an acid, this is going to have to act like a base and gain a hydrogen and gain a charge to make H2O, and I can confirm that on the other side. So I've got my base and my conjugate acid. Right? So just by recognizing, hey, I had HCl here and Cl minus, I've actually cut out a bit of work for me. It works either way if you want to simplify it or if you want to do the whole thing, whatever is easiest for you, right? But look at what would happen if I acted as an acid, what would happen if I acted as a base, okay? And search for what's on the other side. So in practice number 2, you're going to identify the acid A, the base B, the conjugate acid Ca, and the conjugate base Cb in each reaction. Remember, acid and base A and B are on the left side always. Conjugate acid and conjugate base are on the right side always. So go ahead, pause the video, take as much time as you need to do it, and then when you're ready, unpause. Okay, so looking at number 1, I've got ammonia and I've got HCl. So looking here at ammonia, I see ammonium on the other side. So I have gained a hydrogen. That means I'm an acceptor. That's a base, so this must be a conjugate acid. Now if that's a base, this must be an acid. If that's the acid, that's its conjugate base. Okay. It's like once you know one, you can figure all of them out. So looking at this next one, I've got HSO4 minus and then SO4 2 minus. So I've lost a hydrogen. I have donated a hydrogen. So this must be the acid. That must be its conjugate base. This is the acid, that's a base. Conjugate base, that's the conjugate acid. Okay, so far you might have noticed that water is sometimes an acid and sometimes a base. This is because water is pretty special. It's known as an amphoteric substance. So amphoteric substances can act as either a proton donor, so an acid, or a proton acceptor or base, depending on what other substances are present. So near an acid, water will act like a base. It will accept a hydrogen. So that HCl is going to give to the water, and so I end up getting HCl acid, H2O base. But near a base like NH3, water will act like an acid and donate its hydrogen. So I've got ammonia the base and water the acid. Okay. So it just kind of depends on what else is present. Water isn't the only substance that will do that. There are other things like hydrogen sulfate. Right? Here I'm going to show you how hydrogen sulfate, HSO4 minus, will act as a base, a proton acceptor. So I've got hydronium on the other side. It's going to give its proton. And now I've got sulfuric acid and water on the other side. Right? So that was the hydrogen sulfate acting like a base. Here's an example where the hydrogen sulfate is now going to act like an acid when it's near the hydroxide ion. The hydrogen sulfate now will donate its hydrogen, and now we'll be left with the sulfate ion, SO4 minus 2, and water. Right? So depending on what else is present, these guys can go either way. Another special way to define acids and bases is by how many hydrogens it can actually donate. So polyprotic acids, look at the word polyprotic. We know poly is the prefix for many, and protic is referring to protons. So polyprotic acids are acids with many protons. So these produce multiple H plus ions in solution. So something like phosphoric acid here, H3PO4. 3 hydrogens can be removed. So if I were to look into a beaker of phosphoric acid, I would see one phosphate ion and then 3 H's that have come off of it, right, when it dissociates. Now, to be a little more specific, we can talk about diprotic acids. The prefix di means two. So diprotic acids specifically will produce 2 H plus ions. And the most famous example of that is sulfuric acid, which is H2SO4. So yes, diprotic is also polyprotic, it's just more specific. Alright, so now what actually physically makes an acid and a base different, looking at their different characteristics. So for acids have a pH that is less than 7, right? We're going to talk about pH scale in a different video, but for now we'll say their pH is less than 7, between 0 and 7. They are electrolytes. Electrolytes mean that in solution they dissociate. That makes sense, seeing as we're talking about H pluses and OH minuses and things like that. So acids are electrolytes. They have a sour taste. Look at the examples at the bottom, right? Things like citrus fruits and soda, right? That kind of sour pucker your face taste comes from acids. Right? In our next section, indicator colors, right? There are 2 indicators here. Right? An indicator is something that changes color with different pHs. So first one is litmus. Litmus is a paper. There are 2 different versions of litmus paper. There's red and there's blue. So for an acid, the litmus color is red. So if you were to take a blue piece of litmus paper and dip it into an acid here, you would see that litmus paper turn red. Right? If you were to dip red litmus into acid, it would stay red, right? So you want to use the opposite color. Some of you might be curious, oh, why is it crawling up? Remember when we did chromatography, we got capillary action, surface tension, all those things that cause the solution to crawl up the paper. So don't be confused by that. All of this red is due to the fact that it's being dipped in an acid. Now the next type of indicator is called, get ready, phenolphthalein. I'll say that one more time. Phenolphthalein. 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 Phenolphthalein is actually a liquid indicator. So you take a dropper bottle and you drop it into the acid instead of paper. Now, for an acid, phenolphthalein is colorless. Right? Notice I did not say clear. I said colorless. It happens to also be clear. So here is an acid that has some phenolphthalein indicator in it. Notice it looks like any other solution that we really deal with. It's colorless, clear. There's really no change. It's going to be different for a base though. So some common acids. We've talked about sulfuric acid already. That is battery acid. So the stuff in your batteries that helps it conduct electricity is sulfuric acid. Another one, nitric acid, HNO3. That is actually used to make fertilizers and explosives. That's part of why farming is such a dangerous industry. They're dealing with a lot of nitrogen-based things that are highly combustible, right? So it's great for growing corn and for, burning down a building. So phosphoric acid is a food flavoring. You get a lot of phosphoric acid on the back of the nutrition facts on the back of your food packages used in flavoring. Hydrochloric acid is actually in your stomach. It's what helps you digest food. So that acid which is slightly corrosive. Well, not slightly, it's very corrosive. Breaks down your food so that you are better able to digest it and get the nutrients out of it. Acetic acid is your typical vinegar. It's probably, under your kitchen sink, in your pantry right now. We cook with it, we eat it, we throw it on salads. And the last one is carbonic acid, which is actually a byproduct of carbonating water. So when you dissolve carbon dioxide into waters and things like sodas, the carbon dioxide is actually going to react with that water to create carbonic acid. And that is the acid that we get in sodas and actually anything carbonated like fizzy lemonade or anything like that. Okay, so some characteristics of bases. You're going to notice a lot of these are the polar opposite of acids. So the pH of a base is greater than 7. It's between 7 and 14. They are also electrolytes. They produce hydroxide. They have a bitter taste, right? And a slippery feel. So notice my first example is soap. Right? Soap, when you lather, I know a lot of us right now have been getting very used to soaping up our hands for our full 30 seconds. It's a slippery feel when you do it. And I don't know if anyone has ever had their mouth washed out with soap. That was a very classic punishment. Not really anymore, but it used to be. Tastes very, very bitter. Some other examples on there that you might have tasted before, antacids. If you've ever had an upset stomach, you would take an antacid to kind of calm it down. Now, remember what I told you on the last slide? Hydrochloric acid is in your stomach. So when you've got an upset stomach, it's that hydrochloric acid that's causing you pain. So you'll take an antacid, a base, to kind of neutralize that HCl and calm it down. It tastes a lot like chalk. In fact, the active ingredient in Tums is chalk. So, fun fact. Now, the indicator colors. For your litmus is going to be blue. So you would take a piece of red litmus paper, dip it into a base, and you would see blue. Now, that's nice. We've got some, what is it called? It's not assimilation. I'm not an English teacher when all the letters are the same. So you got bases that are bitter and blue. Blue bitter bases. Bitter blue bases. Blue bitter bases. Basic bitter blues. Basic blue bitters. Whatever you want to do to remember there. They all start with B. And then phenolphthalein is no longer going to be colorless. Phenolphthalein in presence of a base is pink. Very pink. Hot pink, some would say. Here is the color of phenolphthalein in a base. Very, very different than an acid. And we'll be working a bit more with that when we talk about titrations a little later. So some common bases. We got sodium hydroxide, which is lye. It's used in detergents and in paper making. Potassium hydroxide is caustic potash, which I have never actually heard it called that before, but it's used in soap. Magnesium hydroxide, MgOH2. This is commonly called milk of magnesia. You can find it in the pharmacy aisle. It's an antacid and also a laxative, so not only will it calm your stomach, it'll very much upset it as well. So some of you might have taken that before if you've ever had medical issues with your stomach. Calcium hydroxide is slaked lime. It's used in sewage treatment and farming. And then ammonia is a household cleaner, which you can probably find in your house right now as well. So notice all of these, with the exception of ammonia, have that hydroxide ion, the OH minus. And we've talked about why ammonia doesn't before. Alright, so the strength of acids and bases. So far we've classified things into the two categories of acids and bases, but not all acids are created the same and not all bases are created the same. So both acids and bases are electrolytes. However, some are weak electrolytes and some are strong electrolytes, meaning the amount that they dissociate in solution will be different. So strong acids and bases are strong electrolytes. They dissociate completely. There are very specific compounds that are strong acids and bases. Your strong bases are any group 1 or 2 element with hydroxide. So here are some examples. Sodium hydroxide and lithium hydroxide. Those are both group 1 elements with hydroxide. They're strong bases. On the other side, we've got strontium and calcium hydroxide. Right? Those are both group 2 elements with hydroxide. All of those and all of the elements in those families create strong bases. Now, the strong acids, there are 5 specific acids that are strong and dissociate 100%. They are HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3 or nitric acid, and H2SO4 or sulfuric acid. Unfortunately, the only thing to do with these are to memorize those 5. Right? So hydrochloric, hydrobromic, and hydroiodic, all 3 of those are halogens, but there's one that is notably missing. The top most electronegative one, which is fluorine. Hydrofluoric acid is not strong. It's actually weak. So weak acids and bases are weak electrolytes, meaning they don't dissociate completely. They only dissociate partially. So the rule here is if it's not strong, it must be weak. So there are a lot of weak acids, right? But there are only those 5 strong acids. So here's the diagram to show you the difference between a strong and a weak acid. So for both of these, we start with before dissociation, all are complete acid. It just uses A and B to represent the strong and the weak. Right? So for the strong acid, after dissociation, I've got all H plus, all A minus, right? You can see all of these are separated up into ions. There is none of my original acid left. A weak acid, I'll dissociate a little into H plus and B minus, right? So there I've got an H plus, here I got a B minus, but mostly it's not going to dissociate. It's going to stay in its original compound, molecule, HB. See, there's an HB, there's an HB, there's an HB. It's still slightly lower, right? I've lost some here. It's dissociated a little bit, but not a lot. How much each weak acid dissociates kind of depends. That's a conversation for AP chemistry. We're not going to dive into that here. Now, the number one mistake I get is between concentration and strength. Concentration and strength are independent of one another. Concentration is based on molarity, right? Remember, moles per liter. We covered that in the beginning of the year. But strength is based on the identity of the acid or base and how much it dissociates. So looking at these examples, starting with 0.3 molar HCl. Well, HCl is on my list of strong acids, so that's a strong acid, but 0.3 is not very high, so that is a dilute but strong acid. Over here, I've got 10 molar HF. Right, HF, remember that is not one of those halogens in my strong. That is a weak acid, but 10 is pretty high. That's a concentrated weak acid. Now I can even look at 12 molar HCl, right? That is concentrated and a strong acid. So you can have any combination of concentrated and dilute versus strong and weak. And here is one diagram to represent the difference between strong, weak, concentrated, and dilute. So a concentrated strong acid has lots and lots of completely dissociated H plus and A minus. Notice there's none of that HA. Versus dilute, it's still 100% dissociated, but there's just fewer of them, right? Weak, we've got lots and lots and lots of HAs, H pluses, A minus, but there's still a lot of those HAs which have not dissociated. Right, so that's why it is weak. The number that I have here makes it concentrated. Dilute, I still have a lot of those HAs, a few H pluses, a few A minuses, but the overall quantity is fewer. Right, so hopefully that'll help you not make the mistake of thinking, oh, a strong acid, it's concentrated, or oh, if it's concentrated, it must be strong. We're going to talk about how we kind of combine strength and concentration when we talk about pH. But for now, this is the end of my lesson on how to define acids and bases.